Hi everyone, JBL EON315 power supply stroke amplifier board. Just a service update, just to detail some of the reliability changes. It seems to me that they get blown up quite often by some people in some locations and not by others, and I think it's to do with the power supply for reasons which I'll explain in a few moments. Now, there is a separate video that deals with the replacement of all these components when they go and what to do if you've got a blown power supply. So if you've got a faulty power supply that's not working, then look at a different video before you get to this one. This one is about improving the reliability, especially with regard to mains surges in the mains. In the UK, the spec is 230 plus 10 minus 6%. Which can theoretically take it up to about 245 volts, but at my house sometimes it's 260, depending when the sun comes out and everyone's panels raise up in voltage and start feeding power into the drain side of the local transformer. The voltage can get quite high, and the problem is that most of the solar inverters have got a limit, are tuned to the UK mains limit so that they can't over voltage your mains. So, but if they start feeding in 3 kilowatts into where your meter basically connects to your main meter, where the consumer unit connects in your house, and if that voltage goes over 2.5, your solar inverter cuts out. So you're not getting any power fed into the grid. You're not getting paid. And so quite a lot of people I've been to someone's house who's had problems, and someone had turned the inverter cutoff limit up to 270 volts. So it would keep pushing up, and it's a problem. It is a problem they haven't really taken into account, actually, especially when the sun's shining and people aren't drawing much power locally because they're all in the garden. But anyway, enough about that. It's a problem. So when you have a main surge, say, there's two kinds of surge, I guess. There's the over voltage surge, where the main suddenly goes way quite high. Say you're running on a generator or an event or something, and someone switches off the floodlights and the generator suddenly is under very little load. You go vroom on the generator. It can't quite react. The regulators can't quite react fast enough to stop the voltage going up to 300 volts AC or something, at which point you've got a problem, because the rectified 245 on this is go through a bridge rectifier, and one end of the bridge rectifier, the positive end, is fed into this end of the cap, one end. These two are in series, and then the negative end of the bridge rectifier on 240 volt supply is at this end. So across the two, you've got something like 320 to 360 volts DC. On 110 volts, it's a slightly different story. If I just show you the circuit, you can see there that there's where live and neutral come in here. You've got a couple of filter caps, which I thought were varistors. If you have a look at this board here and look at these components, you'll see why I thought they were. These little back ones down in the corner, down here, look, they look like the TDK voltage dependent resistors, or the TDK version of a varistor basically, but clearly they're not. They're just those two filter caps. And so what's missing, as you just seen it on the other side of the board as I turned it over, is there's no varistor on this design, none at all. So there's nothing to protect your power supply from a surge on the input, nothing at all. Very strange, don't understand it. If you think I'm wrong, let me know, because I'm still pinching myself saying, can this be true? But it looks to be true. So the first thing we're going to do is stick a 275 varistor, volt varistor, 275 volt AC, which will be a 431K varistor, 431K, across that capacitor. There's a fuse. Obviously, you have to put the varistor on the fuse side of the supply, otherwise it'll be straight across the supply and anything could happen. Bad things probably. Bunch of resistors. There's the common mode rejection choke to stop the switching noise radiating down the main supply and turning your power supply into a transmitter. There's another circuit here, which is another story, but let's go on to the main part of the show, is where we're looking at these components here. So you can see you've got doubler and half V bulk. So in a normal UK main situation, that's neutral on this one. Live comes in here, positive there, DC rectified, negative DC rectified mains there, and it goes along, and basically these two capacitors I pointed out, the big ones, are connected in series across it. And what they've done is, because if you had a differential leakage current, say one cap was leaking more than the other, I'm talking about the DC current that's flowing through that shouldn't be there, they'll drift out. And what they do is they put these 82k resistors in a potential divider to stabilize that central half V bulk. That half V bulk there just goes off to the primary of the switching transformer, and the other end of the primary of the switching transformer goes through a 0.1 capacitor. So everything's fed into the transformer in a quasi-resonant design, so the cap's taking the strain, and this point needs to stay roughly in the center of the supply to make the output work properly, stop it becoming asymmetric. If it becomes asymmetric and you're playing loads of music, one transistor is going to be taking a lot more heat than the other, doing all the work. All right. So if you get a leakage differential, one capacitor is breaking down slightly and it overcomes this 82k resistor, so it only have to be a 200-400 k's worth of leakage, i.e. a DC current path through the cap. Say this one is leaking, the voltage of this one will start to creep up, and you'll pretty soon, in no time at all, over voltage this, and you've got this situation you've had here where it went over voltage and the whole lot just went, because presumably it damaged one of the caps, I would guess, because those caps don't normally fail. Right, so if we go back to the board, so no varistors here either, and I should mention that on quite a few designs, most designs that use the half bridge and this arrangement have a varistor across these capacitors as well. So the varistor you would fit would be a 241k, which is a 200 volt DC varistor, and you can see them here on the back. You can see where I put them. These are just across the caps. They're the 241k varistors, and I'll put a bit of tape underneath just to make sure they don't short out on any tracking or anything else. And then between this and the actual aluminium heatsink there is a card flashover protector, so there's some insulation as well. Of course you've got these components, but these are much higher than those, so it's not going to be a problem with the connections. So a 241k, and then these actually at 200 volts they are conducting slightly. They, it's not a clean shoulder in the function, it kind of leaks and leaks and leaks, and they're nominal 200, so at 200 they will be leaking. So if it creeps up towards 200, these will start to conduct before the capacitors are over voltaged. So I'd advise you to put those two in, and I'd advise you to put that one in, and as I mentioned, take out this relay. That is that relay over here on the schematic that connects doubler and half V bulk. That's the doubling connection. Make that connection, you double the mains, peak voltage, and you can see here's the discriminator circuit here, which is a flip-flop and a comparator, and then a transistor to drive a relay. This relay is the little black relay that I showed you, and you can see doubler and V bulk. Its job is to connect the voltage doubler. So the first problem is the over voltage problem when the range goes high, but the other problem is when you get a dip in the voltage. Now you can imagine if you had a slight brownout, not a severe one, it went down to 110 for a second or two, this switches in the doubler, and when it does that it connects the capacitors to the main, so there's a large spike. There's nothing to limit the current going across that relay, and I've seen quite a few of these little black relays, these things, just with the contacts welded shut, and I put them on the power supply and say, hold on a minute, the doubler switched, and it shouldn't be. If you're on 220, take it out, because these 2 points will be permanently connected, and when you get a brownout and it goes down, this gets confused, switches this relay in, the power comes back, and then you've got the doubler switched in to your mains to temporarily over voltage your cap. So if you're on 230, 220, 240, take the relay out. You don't need it. It's going to cause you trouble. It'll be better without it. All right. So the final thing is always use one of these things if you on a gig, anywhere where you don't trust the mains. If you haven't done the modification, then just get something like this. It's just a mains filter. It's basically a load of those varistors. 13.5, 13,500 amps. You wouldn't have to put that in there for long, would you, to cause it to explode in an electrical explosion? That's a lot of power. Imagine that. That's can only be a spike, can't it? A microsecond or something. So yeah, get one of those and plug this in. Plug your mains lead for your JBLs into this, and then plug that into the lead, and you'll probably get to finish your gig without your speaker blowing up. No, you will. It'll make a big difference. All right. So that's that bit done. Now, switching to another issue. Quite often when these are received, I repair the power supply because it's invariably the power supply. This side of the amplifier is usually doesn't have any catastrophic failures, but you repair this and you get the DC power working and the power supply is fixed, and then you can hear a tick, 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 and that's even with just the ordinary speaker load, the resistive speaker loads, dummy loads, I suppose you call them, fitted and plugged in, and it's the current pulses from this, and it's shorting the power supply, the DC voltage on the power supply. So it tries to power up and then it overcurrents, it shuts down. It tries to power up, it comes back on, it overcurrents, it shuts down. And quite often, as I say, when I've repaired these and I put it back and switch the power on, I can hear this ticking noise, and I know instantly what's gone. And I change these as a matter of course. I never used to, but as I've got to know these things, I change them. All right. And what it is there are two caps on this design which are not suited to their location. They're not happy cappies, basically. Pardon the pun. And the capacitors are, let's get the right one, C113 down here. I've already removed it. I'll show you in a moment. C113 on one channel, and the other one, C213 on the second channel, is just there. That one there. Let's see if I can get a closer view for you so you can have a look. There, you can just see it there. So it's that one there next to the yellow caps, and that one down there, which I've already taken off. Now, it's not a happy circuit. Not a happy circuit at all. If we just have a look at the circuit itself, it's a D-class digital output amplifier, quite efficient. It's actually got pretty good characteristics if you look at the application sheet for this IRS 20955S switch mode Class D output chip for driving a bridge output. So you need a plus supply voltage, which is up here, minus supply voltage up here, two identical devices, N-channel FETs, and then a drive circuit to drive these. Obviously these two cannot be switched on at the same time. If you do, then you just crowbar the actual supply and effects have gone. And what happens on this is that we need, because this is going up and down at something like 50 kilohertz, you know how Class D works. It's kind of a pulse width modulated signal, which is then filtered to produce the average. So this is an averaging filter, first order, to drive that part there at the end will be connected off to your tweeter or your bass, depending on which channel you use. They're both the same, the channels. So there you have it. And I'm not sure on the timing capacitors. I got a feeling that it usually is one of them that's gone. The one that I've removed is the one that's gone, and I'm not sure if the other. I'll have to check that to see whether the other channel is, because of sampling theory. You'd think the bass channel would be running a much slower clock speed because it's less noise, less trouble, less switching losses. Because of the bandwidth, you have to obviously switch at sufficiently high speed to be able to replicate and modulate the output. And if the pulses are too long or the frequency is too slow, then you can't get the resolution in your output. So I imagine the HF channel is running at a different frequency. Anyway, I'm digressing again. So we have to drive this FET. This point is going up and down between the two supply rails here. So we have to make sure that we've got a drive voltage which is registered to this, i.e. relative to the gate source voltage has to be sensible, so we can turn the FET on and we can turn the FET off, and we don't over voltage the FET gate source junction. So what they've got is this cap here, and it goes between the center point, which is the part that's wanging up and down, and here, which is the supply circuit, an isolated switching supply circuit in here for supplying and controlling and the timing and voltages on the gate of this output FET. Right now, if this isn't working properly and this one turns on and this one's half on or something, you just crowbar the supply. But these FETs are very robust. They're kind of the small RF metal can flat pack ones which are on the back of the board. They're under these silicone pads. Well, peel one off for you. It's like after you've been in the sun too long. Look, see? There's one, there's two. I've changed them on one. I bought some, 10 I think, and if I ever design a power supply, I'm going to use those FETs because they don't blow up. They're fantastic actually. I've never seen one except for one where someone had over tightened it and the silicon scab had punched through and shorted on the heatsink. Anyway, I digress. So this cap is in an unhappy situation because it's in a high frequency AC drive circuit. It's high peak currents going through it, and it just doesn't like it. And they're only rated, they're only sort of, these things are only generic caps, I'll show you in a moment, and are rated for 2,000 hours. So I thought, well, yeah, and I was just researching this because this one blew up and I wondered why, and then I looked and found this. Yeah, so I looked and found this. This is the application note for the IRS 20957S. So it's the 5.7 instead of the 5.5. It's pin compatible. There's nothing to worry about. If you can't get the old one, stick a new one in. Or they rarely fail anyway. But anyway, the yeah, basically the same circuit as we've got there. Unsurprisingly, why would you change it? But interestingly, in this document, which is the supporting document, application note, and also the evaluation board that you can buy for about 100 quid. You can just buy one of these and evaluate it for the chip to see whether you want to design it into your design or not. They specify a ceramic capacitor in that position, not electrolytic. Okay. So that is the issue, is that they put the wrong type of cap in. It may have been not clear to them, but it is a major source of failure on these amplifiers. And if you want to see what the document it is, it's the application note and functional description of this chip, which is a replacement for the old chip. Alright, so what are we going to do? Well, actually, what I'll show you now is the caps themselves. The caps themselves that cause the problems. How about that? We'll just do some measurements, and I'll demonstrate the problem by doing a measurement or two. So here they are. Little blighters. Let's see if we can get some tweezers for this. Yeah. So this is what's fitted, is an aluminium can capacitor. Nothing special actually. The Panasonic FP series are very good. If you want a low ESR capacitor that performs at frequency, try the Panasonic FP series of caps. Very, very good indeed. I just usually use those. Sometimes they're too good for some applications. But yeah, 10 microfarad, 25 volt. And this is what we fit instead, which is a 10 microfarad, 25 volt multi-layer ceramic. Now, if you can see the Handtech LCR bridge is connected to these test tweezers. Actually, let's just lock the focus on that. That's better, isn't it? Yeah. So if I just you can see that on the Handtech, you can see where above when my tweezers are there is the 120 hertz, and 120 hertz is the frequency at nearly all electrolytic capacitors are specified. So they have a capacitance at a frequency, and as the frequency goes up, the less perfect a capacitor, the more of a compromised type capacitor it is. As the frequency goes up, the capacitance comes down. It's due to the internal structure, resistances, capacitance, inductances of the actual foil and the configuration of the cap. All right, so you wouldn't use an electrolytic cap for decoupling high frequencies. So anyway, if I measuring 120 hertz, as I say, and we've got the capacitance at the top and the effective series resistance, which is a resistor, a virtual resistor, which is in series with the actual capacitor. And you see we've got 8.2 microfarads, 3 ohms. So it's it had a perfect 8.2 microfarad capacitor, absolutely faultless. This is like having that capacitor and a 3 ohm resistor in series with it on the connection, so it's got an inbuilt resistance. Right, remember that, but the ESR is frequency dependent. as well. You have to remember that. So this is the cap I took out, which was working, but I'm going to change it anyway. And there you have it. We've got 9.674 microfarads with a 16 ohm effective series resistance. Okay, so that's at 120 hertz. Now watch what happens when I put this test frequency up. You can see it's going up 401. So now we're testing the same caps but at 50 kilohertz. And look at the multi-layer ceramic. 8.99 microfarad, 0.17 ohms ESR. So at the operating frequency, that is very good, isn't it? So it's a much better cap at those frequencies. Now if we look at this one at the same frequency, there you go. This at the same frequency you've got 10 nanofarads or something, 10 nanofarads and 260 ohms. So it's not really any good at the frequency. And as the data sheet says, or the manufacturer of the chip says, to use a multi-layered ceramic, I change C218 and C118 for a 10 microfarad 25 volt multi-layer ceramic capacitor, not these shitty things which shouldn't be in there in the first place. Okay, so if you do those changes on these amps, you will eradicate, let's just get rid of that. Yeah, if you do those changes on these amps, you will make them more reliable for you. They have got a bad reputation. I know people are swearing about them, but I understand that in America they're far more reliable because they're working on 110 and they haven't got this Mickey Rouse circuit which gets confused with a shorting relay and no varistors. And on Europe, you know, you're 230 volts, aren't you, roughly? But over here we're 240, and they changed it to 230 and then fiddled around just so we could be European. But the spec isn't the same as Europe. It's just the headline voltage of 230 to 240 was. They like it like that. So I hope you enjoyed that, found that interesting. Service update for this. The EON200, 210s are pretty much the same amplifier circuit. If you're not subscribed already, can you just go down to the little titty button down there and subscribe to me? And if you liked it, also leave me a like, because I appreciate that. It rewards me for what I do. So if you're repairing your 315s, I advise you to do those modifications and you'll be a much happier person.